Hello and welcome to our recording where I'll be explaining how the muscle spindle and Golgi tendon organs function and what their role in motor control is. So, muscle spindles. The muscle spindles are our stretch receptors. There are two different types of afferent endings or sensory endings. We have these annulospiral group 1A afferent axons, and we have our group 2 afferent axons, which are our spray endings, flower spray endings. They both function to sense the stretch of a muscle, but in particular ways, so in slightly different ways. What I want to draw attention to is not just the sensory going into the spinal cord, so away from the muscle and into the spinal cord, but also these motor components. We have our alpha motor neuron, the sprout coming out here and then activating the external muscles, so our extrafusal muscle fibers, our skeletal muscle fiber propers. We also have what's known as a gamma motor neuron. And this is a specialized motor neuron that actually contracts the intrafusal fibers, the fibers inside of our muscle spindle connective tissue bag, if you want to think of it like that. So we're going to talk about not only how we sense muscle stretch, but how we also then contract against that stretch and modulate the behavior or the length of our muscle spindle itself. So with a stretch reflex, what we have, I'll go all the way over to the right-hand side here. We have alpha motor neurons, obviously in charge of muscle contractions. So we might be holding our muscle at a particular length, like here in the middle. We're holding a glass. Now, if we have any kind of disturbance, so the addition of liquid to that glass, as we can see in this second part of the middle figure, then what we're doing is we're creating load. And if we're adding load, then we can get passive stretch. If we stretch a muscle, then the muscle spindles themselves fire off. And the more the stretch and the more rapid the stretch, then we get an increase in afferent discharge rates. That has a positive feedback loop onto the alpha motor neuron pool and the alpha motor neurons in particular that control that muscle. And so what can happen is we then contract against that stretch. So what we see over in the middle here is that at the resting state, our muscle spindle in blue comes in, and we've talked earlier about our ascending pathways, and this ascending information goes up our dorsal column pathway all the way up to the somatosensory cortex. What we also have are these little offshoots, and the collaterals as they're called. Now, the first one comes onto the alpha motor neuron of the actual muscle, so the alpha motor neuron pool of the actual muscle that was stretched. So that's a direct positive, facilitatory, another word to use, effect onto the muscle. So we contract against the stretch. Not only do we have that, we have this inbuilt mechanism by which we have reciprocal activation, it's called, where we get activation of the motor neuron pool of synergistic muscles, so other muscles that can help out with that action. And thirdly, what we get are collaterals onto inhibitory interneurons. And what happens if we activate an inhibitor? Then we get inhibition of our antagonist muscles, and that's our reciprocal inhibition occurring there. And so that then inhibits the antagonist muscles, and in this case, the triceps muscle. So we add the soda in, we get stretch of the bicep muscle, we then get that firing in, we get that afferent volley coming in, and we get a three-pronged attack to attack that issue. We essentially get activation of the alpha motor neuron pool of the stretched muscle, we get activation of our synergist muscles, and we get inhibition of our antagonist muscles. So that's how our muscle spindle at a spinal cord level, our muscle spindle reflex can facilitate movement. So very important reflex loop. And so what about if we talk about those gamma motor neurons? So we were just talking about then these group 1 and 2 afferents going into the spinal cord and having direct input onto the alpha motor neuron pool of the muscle that was stretched. And that then comes back out here and causes contraction of those extrafusal fibers. Now, if that was the end of the story, what would happen when we stretch a muscle is that, and then contract against that. So what we do is stretch, muscle spindle senses that, sends that information into the spinal cord, activates alpha motor neuron pool, and then that sends out to the extrafusal fibers to contract that muscle. Now, what happens if we don't change the length of the intrafusal fibers? You can see here that the muscle spindle has actually become lax. It's all floppy. It no longer has the capacity, if it's flat or floppy, to sense stretch. So we need to reset the spindle, essentially. And you'll notice here that when that original stretch came, it fires off rapidly. That leads to the contraction because of the reflex. But we have this silent period in the middle because it's all floppy. And then by the time the muscle then starts to elongate again, it then kicks back in. What we need to do is we come down here and we look at what happens when we have what we call the alpha-gamma coactivation. Now, we get that stretch, that original stretch. We have that quick succession of 3 action potentials. We then get that contraction of the muscle because of the muscle spindle loop coming back in and activating the extrafusal fibers. But we then also activate the gamma motor neurons in the spinal cord. And those gamma motor neurons, which are slightly smaller and there's a little bit of a delay because they're a smaller motor unit, they come in and they then contract the intrafusal fibers and create a environment whereby the muscle spindle is copying the length of the extrafusal fibers. And that then allows for the muscle spindle itself to maintain a length that is similar to the extrafusal fibers. That means we can fill in that gap and keep firing if any kind of change in muscle length occurs again while we are in those sort of dynamic stages of muscle contraction, elongation, etc. So that's how the muscle spindle works. But the muscle spindle is not the only one functioning. We also have the Golgi-tendon organ. And so the Golgi-tendon organ is actually this network of afferent, 1B afferent neurons that go all the way through the mechanoreceptors that sort of intertwined with the collagen fibers of a tendon. So they're at that the musculotendinous junction, specialized receptor that senses tension within the tendon. So tension is brought about by contracting muscles. We contract a muscle, we then pull on the tendon. That creates tension. Golgi-tendon organ then senses that tension. So when we are looking at our passively stretched muscle, for instance, what happens is we stretch, muscle spindle is going to fire off. Rapid firing because we're stretching the muscle. What's actually going to happen to the Golgi-tendon organ? Well, it fires off a little bit because even under a passively stretched condition, we're going to get some tendon tension, aren't we? So, but it's not going to fire off that rapidly. And what is the effect of that activation of a Golgi-tendon organ at the spinal cord level? Well, if I draw your attention all the way over to the right-hand side here, Golgi tendon, if it's got tension within it, it fires off. It comes in, and again we have that information ascending via the dorsal column pathway. dorsal column, medial lemniscus pathway. But we also then have these collaterals that synapse directly onto inhibitory interneurons that then inhibit the alpha neuron pool of the muscle that's creating the tension. So we're actually inhibiting the muscle that's creating the tension. So it's a bit like the opposite of when we were talking about the stretch reflex. Not only that, but we also have this ability to modulate or even excite the antagonist muscle. So again, the opposite of what happens with the stretch reflex. So we get inhibition of the agonist muscle and excitation of the antagonist muscle. Why might we be doing that? Because it's a kind of like a limiter on the amount of force. And you've got to remember that the human body doesn't necessarily want to produce more and more force. It wants to create a force that is proportional to the requirements of the action, and it wants to protect itself from injury. So then what about when we have muscle contraction that's active? So a muscle is actively contracting, and in particular it's contracting and shortening. Well, muscle spindles, because we have a shortening muscle and it's contracting, muscle spindles are going to largely turn off. They only fire when there's length change, if they're going to be stretched. Okay? Golgi-tendon organs, on the other hand, we start to produce a lot of tension through that muscle and through that tendon. Golgi-tendon organs are going to ramp up their firing frequency significantly. So there's huge increase in firing frequency back into the central nervous system and into the spinal cord. And so if we then join these two concepts together, as in the muscle spindle effects on the alpha motor neuron pool of agonist and antagonists, plus the Golgi tendons, then we see this conflict where stretch receptors want to excite, Golgi tendons want to inhibit antagonist muscles, and the opposite for the antagonist muscles. Muscle spindles are going to inhibit antagonist, while Golgi tendons are going to excite. And so it's important to remember at the level of the spinal cord, what we have is the sum of the inputs onto the alpha motor neuron pools is what goes out. Because you've got to remember that we have these inputs from the spinal level, but not only that, we also have descending inputs onto these interneurons in particular that facilitate the amount of, or not facilitate, modulate is the word I'm looking for, the amount of overall drive that's going from the alpha motor neurons and the alpha motor neuron pool out to the muscles. So the sum of the inputs equals the output in this case. So that there was our short recording on an explanation of what the muscle spindle and Golgi tendon organs do, their function, and their basic role in modulating motor control at the spinal cord level. Thanks for listening, and talk to you soon.